All right, welcome back. In this lesson, we're going to change up our topics a little bit. For the last several videos, we've been talking about discrete distributions and continuous distributions, but both of those scenarios all involve just a single random variable. We usually called it x, but it could have been anything. Okay. Here we're going to start looking at, well, what happens if all of a sudden I want to start understanding probabilities of multiple variables? Okay, and so this topic is called jointly distributed random variables, which basically involve multiple random variables in the distribution. And so that's where we're going to start off with. So kind of like what we did with discrete, we'll set ourselves up to do the discrete first, and then we'll move into kind of continuously distributed. But the discretely distributed, we're going to have a probability mass function again. So our joint PMF then, we define as being the probability of both an x and a y happening. And when we do that, that becomes a probability that my random variable x equals my value of x here at the exact same time that my random variable y equals the y value here. All right, so it's kind of almost, you see that and, that basically makes this thing into an intersection. Okay, and so if A is a set of x and y pair values, okay, then the probability of x and y is in the A set, okay, is going to be then the sum of x and y in A of all the sum x's and y's in A, the sum of their probability. Okay, now that's a whole lot of mathematics terms, and I know you're looking at that going, huh? So let's break this down into an example and try to explain it, okay? Kind of similarly, just for good measure, the joint PDF is the same thing, but instead of the double summation, now I'm integrating over all x and all y. All right, so let's show you exactly what it means, and this will introduce us into some new types of distributions in the process. All right, so I've got a simple example here, a jointly distributed variable distribution in which I have an x random variable and a y random variable, and I've assigned values to x and y. So 100 and 250 are my x values, and my y is 0, 100, and 250. Now what you'll notice is that if I sum all of these, we're back to sum of 1.0. So we have to maintain that because this is my sample space as it's defined. So everything in this table has to add up to 1.0. It's just kind of split out differently now, if you will. And so what you'll see is that, for us, for x of 100 and 0, it's 0.2, 100 and 100, 0.1, and so forth and so on as we look at these values. So that's what a joint distribution looks like. It basically becomes this table that we're kind of starting to look at. So now, if I look for then, say, the probability of 100, 100, that's the point where x is 100 and y is 100. You can see I can look at this table that's the probability x equals 100 and y equals 100. So I come in on this one and I come in on this one. I'm at this value. Okay, so that guy is 0.1. That's all that's saying, and that's what the nomenclature looks like. Okay, now we can go in and look at, well, what's the probability then that y is greater than or equal to 100? Okay, well, if I look at that, well, that would include all of these four values, because this one is y of 100 and this one is y of 250, and so is this one. So I don't care what x is telling me in this case. This is actually what's the probability of y greater than 100. So I would take those four values, 0.1, 0.2, 0.15, 0.3. Those are the values that are here, and if I sum those, I now have 0.75. Okay, would be the probability that y is greater than 100. And again, it's independent of the x. Okay, now we can talk about something called marginals. Okay, and so the marginal PMF then is basically a way of taking a joint distribution and compacting it so that it's only based off of x or it's only based off of y if I don't care about one or the other of the variables. All right, so if we look at, the marginal for x then is the sum of all y values for all the probability values, okay, on that x value. So basically what we're doing is we're going to add the columns. All right, so if I wanted the marginal at 100, I would add this column, this column, and this column for everything on x equals 100. Okay, and then likewise for the y, I can do the same thing, except now I'm summing all x for the probability of x and y. It's basically I'm going to add the rows. So I could turn this into a y equals 0, a y equals 100, and y equals 250 by taking and adding those two guys together. So 0 would get 0.25, 100 would get 0.25, and this guy would get 0.5. And so that would be my marginal in terms of y. Okay, and that's exactly the example that I show here at the bottom. Okay, so the probability, the marginal of x for 100 then is the probability of 100, 0, 100, 100, and 100, 250. So it's all of the x equals 100 pairs. Okay, and so that gives me a marginal of 0.5. All right. Okay. Now for marginal PDFs, okay, it's kind of the same game, except instead of summing, I'm now integrating from infinity to minus infinity. Okay, with respect to dy. Okay, and then for fy, the marginal with respect to y, I'm now summing or integrating with respect to dx. Okay, and as you might expect, if x and y are independent, then the probability of these two guys, if they're independent, then we know that that basically means x and y is the intersection of those 2 points. Then this is the marginal of x multiplied by the marginal of y at that particular point will get you the joint probability. So you can move back and forth. I can explode these things or put them back together. Okay, and then the PDF is the exact same thing, the marginal of x multiplied by the marginal of y. Okay, so this is the discrete, this is the continuous, and we're off to the races at that point. Okay, so let's put one to work and kind of show what a joint distribution looks like. Okay, so what we have is we have a problem where Bob and Annie are agreeing to meet at a restaurant, between 5 p.m. and 6 p.m. Okay, now what we're going to do is we're going to make some assumptions about their behaviors that may or may not be valid, but just for the sake of this argument, we're going to define x and y as independent and uniformly distributed random variables. Okay, so again, keyword is uniform because that tells you what the distribution looks like. Okay, and then independent tells you that they are not coming together, that one's outcome doesn't affect the other, that they're agreeing to meet at the restaurant. So we're going to define random variable x as being Annie's arrival time and random variable y as being Bob's arrival time. So if I draw their distribution based off of time, okay, the Annie distribution we said was uniform between 5 and 6. So it's this case, right? And so this is 1 hour difference, so the magnitude value here is 1.0. Okay, and again, just like for Bob, he could arrive anytime equally likely between 5 and 6, magnitude value 1.0. Okay, so this is the marginal of x, this is the marginal of y. It has nothing to do. So what we want to do is kind of show, well, what's the joint distribution or the joint PDF of this thing start to look like? Okay, and the way that we tackle this is that since they're independent, we can say that the PDF of x and y is going to be the marginal of x, okay, for the x variable multiplied by the marginal of y for the y variable. Okay, and so if I do that, you get something that looks kind of like this guy. Okay, that they both have a magnitude of 1. Okay, so the marginal of x and y is a 1.0 value for x between 5 and 6 and y between 5 and 6. Okay, because that's the only time that they're all going to arrive. Okay, and then it's 0 everywhere else. Now, if I draw this as a sketch, okay, because it's uniform, I can see it fairly easily, that if I plot x and y versus the joint probability distribution on this thing, then you can see that that would be basically the shaded region would be everywhere in which they would meet up. Okay, and then anything outside of the shaded region, if somebody arrived at 4:30 and the other one arrived between 5 and 6, they would never see each other. Okay, so that's kind of the nature of what we have happening here. But the thing to note of this is now that the joint distribution itself is now a surface. Okay, it's not a line, like what we had before. Before we had just this, okay, and that was just a singular line. But now, because of the interaction of this point with all of the points on Annie, so 5 o'clock on Annie means, anywhere from 5 to 6 on the y are all possible values. So every point on the shaded region is a possible value, okay? And so if we kind of look at this, we can come in, that's kind of how we start to calculate our joint distribution. All right, and let me get that off of there. That's not needed, okay. All right, so now let's go through and let's see, let's find the probability that that both arrive between 5:15 and 5:45 p.m. Okay, and so what we're looking for is the probability of x between those two values, 5:15 and 5:45, and y between 5:15 and 5:45. Now you'll notice that with time, mathematically it's a little bit difficult, but in this case we're just going to call that 5.25, and at 5:45 we're going to call that 5.75. All right, because 60 minutes and 15 minutes is 25% of that. So that's the way that we can kind of get around this whole funky time dimension that has to happen here. All right, so all we're going to do then to find this probability is I'm going to integrate with respect to both variables times, and here's my f of xy that we said was 1.0. And if I do that, what this ends up being basically 0.5 quantity squared. All right, it's 0.25. Right, and so that should make sense, right? Because if I had this distribution that was an hour and an hour, the window that we're looking for was this portion of it, right? And this was, a half hour, and so was this guy. Okay, and so what's the total area that exists? Well, the whole thing was 1 by 1, so that's my 100%. So then this is half by half, which is what we were seeing here. So that's the math that's happening behind this. And for a uniform distribution, it's fairly easy because this is a constant, but this could just as easily been an exponential distribution on x, or a log normal on y, and then all I have to do is have those functions that we've defined in the other videos, and I can, as long as I can do the calculus on it, I can tell you probabilities based off of those weighted averages, those tendencies. Okay, so it's basically a 50% chance that each arrives in that half hour. Okay, now if we go in, let's try another one. If the first one to arrive is only willing to wait for 10 minutes before leaving, what's the probability that they actually meet up? Okay, well, we kind of go back, and so kind of what we did with that box idea, we can kind of plot these out again. All right, so let's call this direction as x, we'll call the other direction as y. Okay, and again, it's a 1 by 1 box, that's my 100% on there. So all it's now is figuring out what's the shaded region where this would happen. So what we do is we start to kind of play the game. Well, okay, well, what happens if Annie arrives at 5 o'clock? Then that means that in order for them to meet up, Bob would have to arrive within 10 minutes. All right, and so you'll see that at 5.17, that would be 510 is equal to 5.17 is where that's coming from. So that's the latest that he could arrive for them to meet up. Okay, now if we go the other direction, let's say that they start off that Bob arrives at 5, well then Annie only has till 5:17 to get there. Okay, and so that's the start of how we start to construct this. Okay, everything else then works its way up accordingly. Now what we'll do is we'll jump up to the other end and say that what happens if Annie arrives at 6? Okay, well then Bob, if he's going to arrive between 5 and 6, has to be there, by at least 5.83, 550. If you will, and that will get you this one. Now again, he could meet here, but by then Annie's gone, right? Because they say that we bounded this and said they had to exist in this area. And then likewise, you do the same thing in the other direction. So now it goes from 6 to 5.83. So all I have to do on this is now compute the area of the shaded region, okay? And that represents all of the regions where they meet up. Now again, if I meet here, there's still just that kind of that 10-minute window kind of thing happening off of this. In fact, for a point that's here, okay, if Annie arrives here at this time, then Bob has until either here or here he'll meet her. Because if he arrives here within 10 minutes, she arrives, and then if he arrives here within 10 minutes, they'll meet up before she leaves. So that's kind of this double band 10 minute thing starts to happen here. So it's a vertical band 20, and you can play the same game going this way as well. Okay, for the Annies and the Bobs in the reverse direction. So it's kind of a way to kind of look at it, but there's kind of this symmetrical band, if you will, that starts to kind of live down that line. Okay, that kind of represents kind of the half region, if you will. So a lot of times, a lot of these problems, they'll work on a half region instead of the full as a nature for it. Okay, all right. So the question becomes, well, how do we compute the area? Well, if we do it with the equation form, you get something that kind of looks like this. All right. So I get so to represent all of those areas, that we can do a double integral from 0 to 5.17. So again, that's 5:10 p.m. And then from whatever y value to y plus 10 minutes. Okay, and then of 1, that's my f of x, y value, dx, dy. And then I can do from the middle band that goes from 5:10 to 5:50, and then I go from y minus 10 minutes to y plus 10 minutes. That's what we were just saying, multiplied by 1. Okay, and then plus the last region, which is 583 to 6, and then y minus 0.17 all the way up to then the upper bound of 6 on that one. Okay, and if I do the math on that, that becomes 0.31 is my math on our scenario there. Okay, all right. Now, we could also do it a different way by saying that since I know this whole thing is 1, okay, and I know that this is 50 minutes, and I know that this is 50 minutes, and I know that this is 50, and that's 50, and then of course these little chunks are 10, okay, I could just as easily have taken 1 minus and subtracted off those two little triangles. And if I do that, if we go in and start to look at that the probability of my shaded region, because again, that's what I'm looking for, is 1 minus number 1 minus number 2. So it's 1 minus, and this is going to be 1/2 of my 50 minutes is 0.83 hours, and then 0.83, so it's 0.83 this way, 0.83 that way. It gets me this term, and then I do the same thing on the other corner. And if I do it, I get the exact same numerical math number that we got up here. It's 0.311 and 0.311. Okay? All right, so that's what we have for that one. Okay, the next one that we do a little bit with, just so that we can kind of finish out the notes, okay, has to do with the conditional PDF. Okay, and so this is going to be my PDF of y given x happening for the event y given x is the joint probability divided by the marginal of the given. Okay, so if I need the given x, and I'm taking the marginal of x. If I need the given y, I'm taking the marginal of y, and so forth and so on. Okay, and also note that if f, x, and y are independent of each other, then the conditional of this one is equal to fy. Okay, that his basis isn't anything to do with that conditional in that tree branch. Okay, and if you look at what we had before when we did conditionals with the discrete system, probability of A given B was the probability of A intersect B divided by the probability of B. If you look at this formula, it's the exact same. Here's the intersection, and here's the singular event for the given. The B was on the right, B, X, X, it works. Okay, so it's very, very similar in approach to the way that you expect to kind of do this. All right, now, where joint distributions are different is in the area of expected value and the variance. Okay, because what happens is that when we had single random variables, when we were just dealing with x, all we had was an expected value and a variance or a standard deviation, one of the two. These were the two defining parameters that defined your distribution. With joint random variables, we now have an expected value again, but now I have what we call as a covariance as well as a correlation. Okay, because remember, variance is kind of measuring, if we have this, and this was my mean, we were kind of trying to measure that distance, right? It was kind of an estimate of what the variance was. Well, now, covariance, I'm doing this in two directions. So we've got to come up with a slightly different formula for that. All right, so the expected value isn't really any different. It's kind of what you would expect on this. So I've written the general form, which is the expected value of a function of x and y is the integral over infinity to minus infinity, and you do that on both integrals, of the functional equation multiplied by the probability distribution function. So h of xy times f of xy, and then I integrate it with respect to x and y over all and over the entire domain. So that's basically the same as what you saw before. There's no real surprise. The covariance, on the other hand, is a little bit different. Okay, and this is considered to be a measure of linear independence. Okay, now the covariance of xy is basically the expected value that we had before. If you remember, when we did the variance of x, it was the expected value of x minus mu, that whole thing, quantity squared. All right, so what the covariance is doing now is it's basically saying, well, you had two of them here. That's what that squared was. Is you keep one as x minus mu x, and then I'm going to compute the other one as y minus mu y. So it's x minus the marginal of x and y minus the marginal of y will get you the covariance of x and y. Okay, and if you expand this thing out, this is what it looks like. It's kind of this long expanded property. So the double integral from infinity to minus infinity of x minus mu x times y minus mu y multiplied by the probability distribution function will get you the covariance of those values. So you can see it gets a little cumbersome to compute. They do have a shorthand version. Remember, before we had the var of x, we said could also be written as the expected value of x squared minus then the expected value of x squared. That was for the single. Well, covariance, all I do is I take this equation and I take one of the x's and turn it into a y, and then take one of the x's and turn it into a y. Okay, so again, here's our discrete formula, and so it's the same game. So that's a pretty handy little conversion there. So let me get that off of there, so it doesn't come through on the notes. Okay, and we're back to the game. All right. Okay, now here's one of the little tricks on it. Okay, if x and y are independent, okay, then the covariance of x and y will be equal to 0. Okay, however, if you compute the covariance of x and y and come up with a 0, it does not necessarily mean that they were independent. All right, because again, we're subtracting things, and I could zero out any one of these terms, and they could be related to each other. But if you know that they're independent, then you know covariance of x and y is going to be equal to 0. All right, now you'll notice that this formula is not real hard, but it's useful. It kind of helps give you a gauge of the spread of the data. All right, but to kind of help us out, they come up with a different correlation because if you remember, variance could be any number based off of the distribution, and so could covariance. All right, but what has more meaning to us then, it has to do with what they call a correlation. Okay, and that's a specialized or a normalized covariance. So we're going to take that covariance equation and we're going to modify it and basically shrink it down and normalize it. Okay, and so we're going to do the correlation of x and y, and typically this is written with the Greek symbol rho. Okay, so the rho of x and y, or just rho, is going to be the covariance of x and y divided by the marginal standard deviation of x and the marginal standard deviation of y. Okay, and if I do that, then what will happen is this guy this rho value, and one of its properties is that it lives between -1 and +1. It can't ever exceed that. So if you've ever done any sort of curve fitting in Excel and looked for those R values, this is a representative of that R, right? The closer you were to 1, the better the direct correlation on the data was, okay? So if X and Y are independent, rho is 0. If rho is equal to positive or -1, then there is a linear correlation that exists. All right, and so the way that I remember this is I make some general plots, all right? We can say that we have a positive covariance if as X increases, Y also increases. And imagine I'm trying to fit a line down through the data, the best fit linear value on this, okay? This is a tendency of rho going to 1.0, that linear relationship, okay? Rho is going to +1, means that as X goes up, Y goes up, okay? And then the converse of this, the negative covariance, is rho going to -1, okay? In which as I increase X, Y goes down, or vice versa. As I, increase Y, then X goes down as a result of it. Would be a different form of it. Okay, and then the covariance near 0, or a rho of 0, is basically your old scatter plot. There is no best fit line. Here I had a line that could come fitting down through there. I don't get that line here. Okay, so it's kind of this scatter shot kind of value for covariance when rho is equal to 0. So anyway, it's kind of a picture that kind of helps me visualize what's happening on those. So anyway, we'll go ahead and end that one there. So that's kind of some joint distribution properties. Hope it made sense to you. As always, if this helped, leave us a comment down below. Please be sure to like the video, and as always, subscribe to the channel if you would. Have a great evening, and we will see you all next time. Happy engineering.